Hello everyone, welcome to lesson 1 of A-level physics. In this lesson we're going to start with one of the most important foundations in physics, physical quantities and units. Before we rush into equations, calculations and problem solving, we need to understand the language that physics uses. That language is built from quantities, numbers, and units. A very important habit in physics is this: do not just look at the number, always look at the unit. If the unit is wrong, the answer may be physically meaningless, even if the calculation looks reasonable. So today we will learn what a physical quantity is and what SI-based units are, how derived units are formed, and how to use units to check whether an equation makes sense. Here is the structure of today's lesson. We will first see why units matter, then define physical quantities, introduce SI-based units and derived units. After that, we will use units to check equations, and finally we will finish with a few quick practice questions. Let's start with why units matter. Suppose a student writes velocity equals 20 meters. At first glance, this looks like a physics answer. It has a number, it has a unit, but it's not acceptable. The problem is that meter is a unit of length or distance. Velocity is not measured in meters. Instead, velocity is measured in meters per second, written as ms to the power of -1. So this answer confuses velocity with distance. This is why units matter. Units are not decoration at the end of an answer. Units tell us what kind of physical quantity we are dealing with. Now look at the number 20 by itself. What does 20 mean? It could mean 20 meters, it could mean 20 seconds, 20 kilograms, or even mean 20 degrees Celsius in another context. The number alone doesn't give us enough information, but when we write 20 meter, 20 seconds, 20 kilograms, the meaning becomes clear. In physics, a number without a correct unit is usually incomplete. This is especially important in exams. Even if your numerical calculation is correct, missing or incorrect units can cost marks. So, from the very beginning, please build this habit. Every measured quantity should have both a value and a unit. Now we can define physical quantities more carefully. A physical quantity is something that can be measured. Examples include length, time, mass, temperature, electric current, force, velocity, and many others. A physical quantity has two parts: a numerical value and a unit. For example, length equals 2.5 meters here. 2.5 is the numerical value and meter is the unit. So, the same meaning in the next three quantities shows the same. So whenever you write a physics answer, ask yourself, have I included both the value and the unit? Before we go deeper into units, let us briefly introduce two types of physical quantities: scalars and vectors. A scalar quantity has magnitude only. Magnitude means size or amount. Examples of scalar quantities include mass, time, temperature, and speed. A vector quantity has both magnitude and direction. Examples of vector quantities include displacement, velocity, acceleration, and force. For this lesson, you only need the basic idea. Some quantities need only a size, while others also need a direction. We will study scalars and vectors properly in the next lesson because this distinction becomes very important in mechanics. Now, let's move on to SI base units. SI stands for the International System of Units. These are the standard units used in science. You can think of SI base units as the building blocks of physics units. There are 7 SI base quantities: length, mass, time, electric, thermodynamic, temperature, amount of substance, luminous intensity. In A-level physics, the most common base units you will see are meter, kilogram, second, ampere, Kelvin, and mole. Candela appears much less often, but it is still one of the 7 SI base units. And this slide shows some common units you will meet in A-level physics. Distance is measured in meters. Time is measured in seconds. Mass is measured in kilograms. Speed is measured in meters per second, written as ms to the power of -1. Acceleration is measured in meters per second squared, written as ms to the power of -2. Force is measured in newtons, symbol N. Energy is measured in joules, symbol J. Power is measured in watts, symbol W. Pressure measured in pascals, symbol PA. At this stage, do not try to memorize every unit as a separate fact. The more powerful idea is that many result units can be derived from equations. Now, let's see how new units are built from these base units. Let's start with speed. Speed is defined as distance divided by time. Distance is measured in meters, and time is measured in seconds. Therefore, the unit of speed is meter divided by second, written as m/s. This is normally written as ms to the power of -1. The negative power means per, per. So s to the power of -1 means per second. Now look at acceleration. Acceleration is the change in velocity divided by time. Velocity has the unit ms to the power of -1. If we divided that by another second, we get ms to the power of -2. So acceleration is measured in meters per second squared. Now, let's see where the unit Newton comes from. Newton's second law states that force equals mass times acceleration. In symbols, F equals ma. Mass is measured in kilograms. Acceleration is measured in ms to the power of -2. So the unit of force is kilogram, kg, times ms to the power of -2. That gives kg ms to the power of -2. We call this unit the Newton, symbol N. So 1 Newton is equal to 1 kilogram meter per second squared. This is an important point. A named unit is often used just as a shorter name for a combination of base units. Now let's look at another typical example. Density. Density is usually represented by the Greek letter rho. The formula for density is mass divided by volume. Mass is measured in kilograms. Volume is measured in cubic meters, or m cubed. So the unit of density is kg divided by m cubed. This can be written as kgm to the power of minus 3. Be careful here, the minus sign is very important. Kgm to the power of minus 3 means kilograms per cubic meter, but kgm cubed would mean kilograms times cubic meters, which is not the unit of density. This is a common place where students make mistakes in exams. Now we will use units as a tool to check equations. Consider the equation of motion. S equals plus ut plus 1/2 s squared. Here, S is displacement, so its unit is meter. For the equation to make sense, every term on the right-hand side must also have the unit meter. First, look at ut. U is velocity, so its unit is ms to the power of minus 1. S is time, so its unit is s. When we multiply them, ms to the power of minus 1 times s gives m. So ut has the unit meter. Now look at the squared. A is acceleration with unit ms to the power of minus 2. T squared has the unit s squared. Multiplying them gives ms to the power of minus 2 times s squared, which equals m. So s squared also has the unit meter. Therefore, the equation is dimensionally consistent. Unit checking is a very useful habit, but we need to understand what it can and cannot do. It can help you spot impossible answers. For example, if a velocity answer has the unit meter, you know something is wrong. It can also help you catch missing powers, such as writing s instead of s to the power of minus 1, or writing m cubed instead of m to the power of minus 3. It can also help you check whether an equation is reasonable. However, unit checking cannot prove that an equation is definitely correct. It cannot also prove that your numerical answer is correct and prove that your method is complete. So use unit checking as a quick and powerful test, but do not treat it as a full proof. Let's finish with some quick practice. Let's try these 3 quick practice questions. Please pause the video here and try the questions before looking at the answers. Let's go through the answers. For question 1, the SI unit of acceleration is ms to the power of minus 2. For equation 2, we start from Newton's second law, F equals ma. Mass has the unit kg, and acceleration has the unit ms to the power of minus 2. Therefore, force has the unit kg ms to the power of minus 2. For question 3, density is mass divided by volume. Mass is measured in kg, and volume is measured in m cubed. So density should be kgm to the power of minus 3, not kgm cubed. The negative power means per cubic meter. Let's summarize the key ideas from this lesson. First, a physical quantity has a numerical value and unit. SI-based units are foundation of physics units. Derived units are built from base units using equations. Unit checking is a powerful way to test equations and answers. And finally, units are not decoration, they are part of physics. If you build strong habits with units now, your later work in mechanics, electricity, waves, thermal physics will be much more reliable. In the next lesson, we will study scalars and vectors. We'll explain why speed and velocity are not the same thing, and why direction matters in physics. This is especially important for mechanics where displacement, velocity, acceleration, and force are all vector quantities. Thank you for watching. You can find the channel at shughwang. If you have any questions, you can contact me by email at shughwang@gmail.com. See you in the next lesson.